Okay. First off, a couple announcements. Oh, you need help or are you good, Hayden? Are you good? You need help? So the first thing is I'm not going to allow any more quiz retakes after a certain date. So let's look at the schedule. I think up till study week, and the reason for that, not retakes, sorry, I'm not offering retakes. It's for if someone didn't come to class, and it's supposed to be because they were sick, making up quizzes. I know that it's been abused, but I had to do it. And then I want to stop giving them on this day. So that will be the last day, because study week I want to post a PDF of every quiz from the beginning till the end in case people lost their quizzes or whatever. So there will be just a PDF with every quiz one after the other so that you can use it as a study tool. Like you can solve them as practice problems. So after April 27th, there will be no more quizzes that can be made up in my office if you missed them. Okay, because I'm going to post all of them. That's one thing. Another thing is I know a lot of people have come to me asking about their grade. As much as I'd like to curve, I can't because so many people are doing fine. So I can't curve your grade from an F to a passing grade. If you're in the F or D range, come see me. I ran a little column in Excel which outputs what your maximum final grade is at this point. Several of you are kind of beyond the point of no return. Like even 100 on everything wouldn't be enough to pass. So if you think that might be you, come see me in my office and we can talk. But I can't curve. Like there's too many high grades. It wouldn't be fair. And then the last thing is I'm not giving a quiz today because I just want to review RC and RL circuits and all those concepts and try and kind of get us all on the same page regarding that stuff. So I guess today will just be kind of a review of RC and RL stuff, even just capacitors and inductors. And I can either open up to questions that anyone has. We were talking about this in my office today. I know a lot of times you might not even know what your question is, but you're just confused. And if that's the case, just raise your hand and tell me you're confused so that I'll re-explain it. Because if I end up with a room full of people that are confused and I keep going, it's not productive. I'd rather stop and figure out what's confusing you. All right? So today we'll just review. We're going to go over stuff. And if we run out of things to go over, then I'll start AC. But I don't think we're going to run out of things to go over. However, the next homework, the next homework is due Monday. It's a little bit of RL circuits, just like a similar problem to how we had the RCR problem. It's the RL problem. You should be fine. I don't think it's very difficult. And then I did start asking questions about AC. So when we get an hour in, I might take the last 10-15 minutes to just explain this so you can do this. This is not difficult. This is just showing how signals are represented in the AC domain. And each number has a meaning, and I'll just explain them so that you can do this part of the homework. Okay? So with that being said, I guess we'll start with just, are there any questions about this past homework, this one that was due today? Yeah, you have a question?
Well, I just had a question about understanding it. On A, 3A, Spice gave me 20 milliamps was like what my current was supposed to go to, but like I got 24 milliamps.
It should be 20 milliamps because in steady state, I'm going to have 5 volts across a 250 ohm, which would be 20 milliamps. So I'm not sure why it would be 20. Yeah, so it should be 20 milliamps. So maybe something was off in your spice.
Oh, yeah, I can't remember.
What was it?
I don't know why. I don't know if I just didn't calculate, but like for some reason I got 24.
Like the only way I could see you getting 24 is if you put 6 here.
No, I think we're good. I think we're good. That
All
was
right.
just a mistake I made.
Yeah, so in steady state, right, there's 5 volts here, and then, by the way, I say steady state all the time. I just assume you know what that means. Steady state means nothing's moving. Everything's steady. That's all it means. So, like, basically, any DC circuit that we analyze is a steady state circuit. It's in steady state. AC circuits like this, well, this is technically an AC circuit, but we're not using AC signals. They're not in steady state when the switching occurs. Basically, everything gets disrupted and voltages and currents start moving, and then when they all settle, that's steady state. So whenever I say that, just know that I mean nothing is moving, okay? So in steady state, right, when this is 5 because this acts like a wire in steady state. And then 5 volts over 250 gives me 20 milliamps, right? All right, so any other questions about this homework? All right. Okay, so...
I got a question.
Oh, yeah.
Just because I don't really understand why, and I messed this up on the homework, 15 actually. 15 had basically one without that. Well, we can look at the same one.
This one?
Yeah. So why does... I don't really understand why you need to have a resistor with the inductor. Like how, like exactly what that relationship does that causes that drain that's supposed to happen. Because like what I had done on mine is I added a switch. It got my voltage to go back, but I missed it draining the current like it was supposed to. So I guess I'm missing something there with like that relationship.
So the tau, right? The tau for charging or discharging an inductor is L over R.
Yeah.
So if R is 0, basically...
Oh, okay. I didn't think about looking at it like that.
Yeah, we're basically we're setting how long it's going to take to discharge, and so if L over R is small, then that means it discharges really, 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 really fast. And if we give it no no resistance, then my discharge time is like 0.
So it's not going to.
Or sorry, it would be infinite, right?
Yeah.
L over R, yeah. If R is 0, then it would be an infinite time because technically it can't discharge anywhere. You don't necessarily have to give it a path, but what that's saying is if I had 0 here and it takes an infinite amount of time to de-energize, that means it would never de-energize, right? And the reason for that is that if I close this loop and I don't have any resistance here, there's nowhere for the energy to be dissipated. So theoretically, obviously this wouldn't actually happen, the current will just loop forever in this loop and it will never stop. You're not actually de-energizing the coil. But because SPICE has parasitic resistances, and like I talked about last time, an open switch still has some like giga ohms of resistance, it will not behave like, it won't just keep looping forever. But what's happening theoretically is that you're not actually de-energizing the coil. You need somewhere to dissipate the energy. And we know, right, well, I don't know if I said this, maybe I didn't say this. Capacitors and inductors don't dissipate power, ideally. They just store energy. They don't actually dissipate any energy. Okay? But resistors do. So if we want to dissipate that energy and basically de-energize the circuit, we need the resistor to dissipate it.
Okay, that makes sense.
All right? Yeah.
But that's only the case technically in ideal circuits like in LT SPICE, because otherwise if we have a wire, it has an innate resistance, correct?
Right. So in real life, if you were to do this, your wire would have a resistance,
Right.
but the resistance is so low that the time would still be really long, so you'd get this looping. It would happen. And what would probably happen is you end up with, I don't know how much current was flowing in this case. What was it? Like 2.4 milliamps or something? Is that right? So you get 2.4 milliamps flowing, and your resistance is minute, like it's basically nothing. Your wires could burn because there's nothing limiting that current.
Right.
Trying to think of the power equation. It's I squared times R. Yeah, that doesn't make any sense. I don't know exactly what would happen. I do know that you're right, though, that it would dissipate because there is resistance in the wires. Resistance and conductance are inverses of each other. Everybody knows that. So if something's more resistive, it's less conductive. If it's more conductive, it's less resistive. So wires are conductors, and they're really, really, really conductive, but they're still slightly resistive, right? If you measure, the resistance of a really long wire, you'll get like 0.4 ohms or something, but there's still resistance there, and it's quantifiable. But yes, you're right. Anything else on this? All right. Okay. So maybe, does anybody have any questions about RC circuits or about any of this stuff, or is there anything that's bothering you particularly? Otherwise, I'm just gonna have to like go back to RC circuits and guess what's bothering you. Yeah.
Can you go over again, like, how inductors work?
How inductors work?
Yeah, is that possible?
Yeah, I can go over it again. Maybe I should go over how capacitors work and how inductors work side by side,
Yeah.
so that we can see all the like similarities and differences. All right, let's see if the camera likes me today. Well, let's see if it likes whoever's method this was for putting the light there. Dara. All right. It's not doing anything crazy, right? Oh, there it goes, out of focus. Okay. Is it not focused?
It's just a tiny bit blurry.
Should be fine. I'm gonna get two colors. I'm gonna get like two very different colors so that we can compare them. I'm gonna get this out of my way. Sorry, it was a cool idea, but it's in my way now. If it's doing it, it's still doing it. Why? Why? I just don't get it.
Why did it start now?
It started last time on Monday. I don't know why. It's been fine. What's funny is that like before the class started, like in the, what was it? Is this the spring? In the winter, when I was messing around with this, it was doing this. And then when I started teaching, it just decided to stop. And I was like, oh, okay. Cool. And now it's back. All right, so inductors, let's go. So that's the symbol. It's measured in henries. We know this. I'm just going to go back and forth. I guess there wouldn't be an apostrophe, but too late. So inductors store energy as a magnetic field. A lot of this should feel like review because it is. And capacitors store energy as an electric field. All right. Inductors resist changes in current, right? Capacitors resist changes in their voltage. And by their voltage, I mean the voltage across the capacitor, right? All right. Let's see what else. Okay, so now I should probably write the equations. So we know that the capacitor current is equal to the capacitance times the rate of change of the voltage. We know that the inductor's voltage is equal to L times the rate of change of the current. All right. A capacitor is made of two conductive plates with a dielectric in between. Dielectric is something that's not conductive, but it boosts the strength of the electric field, which lets us store more charge for the same size capacitor. So that's basically like the equivalent of the magnet that the wire is wrapped around for an inductor, right? So made of two conductive plates with a dielectric in between. And then the inductor is made of a wire wrapped around a magnetic material.
Inductors are solenoids, right?
Yes.
Yeah, I think they're the same thing. Yeah, so we use the solenoid in our senior design project. It's basically a circuit, or it's a type of component. There's all kinds of solenoids. There's push type solenoids, like when you energize them, they'll push out. There's pull type solenoids that when you energize them, they'll pull back. And then there's pneumatic solenoids, which basically have like a mechanical switch inside. So when you energize the coil, you get a magnetic field forms, and two contacts will make a contact. You can have a switch that works that way. You can have pneumatics that work that way, basically that either allow air to flow through or not allow air to flow through based on whether or not the coil is energized. And all of this is working based on two metals that are either touching or not touching when you energize or de-energize the solenoid, which is just another word for the coil. Okay, so store energy as yeah. All right, any questions? Yeah.
Can you go over like how the difference is, like when it charges and discharges?
Yeah, so I guess the important piece here is this, like for both of them. I can't really star that one. It's basically this row right here. This is what's important. This is what's important for how the circuits work. Because everything that happens in the capacitor circuit is a result of the fact that their voltage doesn't want to change. And everything that happens in the inductor circuit is a result of the fact that their current doesn't want to change. So everything else in the circuit acts accordingly. Okay? So, I'd have to just do examples. Is there any particular problem that bothered anybody from the homeworks, or you want me to work the last quiz? Is that fine? The quiz from last time? Alright, let me grab somebody's. I'm going to grab somebody's who did well so I don't embarrass anybody.
Try mine.
This one's good. Well, I'm not going to put it under this thing anyways, but just in case somebody sees it. Alright, so let's just... Any questions here before I... Yeah.
So on a waveform, you'll never see a capacitor or inductor have a drop.
On a waveform for a capacitor, you'll never see the voltage across the capacitor change suddenly. Ever. Unless you're forcing it to, right? By like discharging it immediately, which you're not supposed to do, which causes problems. On an inductor, so in SPICE, no. In SPICE, no. On an inductor, you'll never see the current jump immediately because it can't. And if it does look like it's jumping immediately, zoom in. It's probably jumping really, 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 really fast and doing an RL thing, right? But ideally, no. You should never see the voltage across a capacitor jump. But note this. It's really easy to see with the inductors, because when we plot the current in LT SPICE, it's just one trace. But if you wanted to plot the voltage across a capacitor, you have to plot both sides of it, right? You can't, or you ground one side and then you just see the voltage across the capacitor, because, right, VC, the voltage across the capacitor, is the top plate minus the bottom plate. And so you might see the top plate jump suddenly, but you won't see that unless you also see the minus plate jump suddenly, because they have to go together, because the voltage across it can't change instantaneously. Does that make sense to everybody? If it doesn't, let me know. Alright, so what I just said basically is the capacitor, right? Here, let's just do it in SPICE. And then I'll come back to the inductor and I'll do the quiz. But real quick, let's go to SPICE so we can look at this. What homework was the capacitors? Like homework 12? No, those are all inductors, I think. No, yeah. Alright, so for example, let's look at this circuit. I'm going to have to sit closer to the camera or it's not going to hear me. Alright, okay, so let me comment this. Let's just, All right, so let's take a look at this. So basically, if I were to talk about the voltage across the capacitor, I have to take one side minus the other side. Is everybody comfortable with that? The same way we talked about the voltage across this resistor. If I were to take the voltage across this resistor, does this make sense? Raise your hand if it makes sense that V in minus V out is the voltage across the resistor. If it makes sense, raise your hand. All right. So then it would also make sense that the voltage across the capacitor would be V out minus 0. Right? So it's the top plate. Here, let me just, I just want to make this super clear. This is the voltage across my capacitor. That is what I'm talking about. Cannot change instantaneously. It can't. Okay? The voltage across it. That does not mean that the voltage here can't change instantaneously. If this changed instantaneously, this would have to change instantaneously with it. Because then the plus minus the minus would not change. Right? That difference would not change. In this particular circuit, the minus is connected to ground. So the minus cannot change at all. Which means that the plus will not change instantaneously. So if we run this, the plus doesn't change instantaneously, right? It starts going up at this exponential. That's because the minus can't change. So in order for, if I were to plot like VC in this case, I would have to do V out of A minus 0 basically, which is the same exact waveform. Okay? So just keep that in your head. Now let's do another example. This exact same circuit. I'm going to have to change these though. And I'm going to switch the capacitor and the resistor. So now my tau is exactly the same. Ugh, this is so horrible. My tau is exactly the same. Everyone agrees that my tau has not changed. I have the same R and the same C. Now, my voltage across my capacitor is this. It's this minus, you know what, I might as well just delete it. That is now my voltage across the capacitor. V in minus V out is my voltage across my capacitor. Okay? So now, again, I said the voltage across the capacitor cannot change instantaneously. In this case, initially, V in is going to be 0. Hold on, I got to change this too. V in is going to be 0 before the pulse goes high. And then it's going to shoot up immediately, which means I am forcing one of the plates of the capacitor to jump up immediately. So that this difference does not change instantaneously, the other plate has to jump up with it so that that difference doesn't change. It went from 0 minus 0 to 5 minus 5. In both cases, it's 0. Everybody, is that clear? So when I run this other circuit, V in jumps, and V out also jumps. So let me make some new, hold on, I gotta go back to what you said, right? This? Nice. Okay, so let's get this one off there now. V in jumps, V out jumps, okay? So now let me add another plot plane. We haven't done this yet. I should have done this a long time ago. I'm gonna take V in, that's not what I wanted to do. My gosh. Exit. Alright, so basically I just need to come up here, click on that, then I can click on V in. Now I have V in, and I want to get V in minus V out. That is the difference across my capacitor. I can plot that. V out, A2. Do you see that? It doesn't change instantaneously. Right? It takes the exponential path. The input is changing, it's jumping up instantly. The output is changing, it's jumping up instantly. But if I take that difference, that takes the path that we're expecting to see. That is the charging equation. Does that make sense? Does this make sense? Does anybody have any questions about this?
Does Spice just let you plot like capacitor to show if you have to do it like that?
This spice let you do what?
Like, could you have just clicked on the capacitor for it to plot does that already have to do it that way?
If you go to click on the capacitor, it gives you current. Every time you go to click on the component, it'll give you current. But if you want to plot the difference across anything, this is how you do it. You just subtract. So that's something that's my fault. I should have showed this a long time ago. I say things and they're clear to me, but they're not clear to you. So does that make sense? Everybody thinks this makes sense? If it doesn't make sense to me, we can go over I can re-explain it. Yes.
So, obviously, you could just use Fife if you wanted to, to calculate V out A2, you could just use the Fife equation to see what is going on there, correct?
Yeah.
But if you weren't to do that, you would have to use the charging equation despite the fact that it's going down.
No. I mean, in this case, if you're talking about this, it depends on the waveform you're talking about.
I'm talking about the waveform for V out A2.
This one. You would definitely use the discharging equation.
Okay.
Because the discharging equation is used when you're going from an initial value that's higher than your final value.
Okay.
And the charging equation is used when you're going from an initial value that's lower than your final value, right? When you're going up, we call that charging. So technically, the capacitor is charging because one side is fixed and the other side has to discharge.
Okay.
But it's not. So we call this the discharging equation because we're talking about capacitors, but you could call it like the decreasing equation if you want to think of it that way. This node's voltage has to decrease in order for the capacitor to charge. Does that make sense?
Yeah.
All right. Okay. So any questions about this? Otherwise, I'm going to go do yes.
So you use basically Fife and then function of the initial and the final.
Yeah, I think the hard part for pretty much everybody is figuring out what the initial and final values are. Right? That's the hard part. It's not plugging into the equation. It's not plugging anything in after that. It's determining how the hell do I know what's the initial and what's the final. Okay? And in order to understand to know what's the initial and what's the final, you really truly have to understand what happens in the circuit, right? You have to understand that when I send this voltage up to 5, right? So when I send V in up to 5, in this case, V out has to go up to, V out's going to stay at 0 in that case, right? Because we can't. Yeah. Hold on. Didn't we just do this one?
I'm on the right side.
Am I looking at the wrong plot?
Yeah, look at the right side.
Okay.
Right side.
So if I send this up to 5, I know, and you have to know, or you're not going to get this problem right. You have to know the capacitor voltage cannot go up instantly. Which means if this goes up to by whatever amount, this has to go up by the same amount so that difference can stay the same, right? If I make this 50 volts, let's just for the hell of it, 50 volts, right? And I run this, it's not going to look like anything changed. And the reason it doesn't look like anything changes is because my input goes up to 50, my output spikes up to 50 right there with it because that difference is still 0, right? And I think that another thing I think we talked about in my office hours today is that it's hard to understand why are we getting 50 volts over here if there's no source there. Like, where is that 50 volts coming from? I mean, again, voltage is just a measurement of how much potential energy is at that point in the circuit. At that node, we have 50 volts of potential. If we were to connect something there and try to power it with that 50 volts, it would go immediately to 0. It's not a power supply. That's just what we would read on our multimeter if this happened in the circuit for that one moment. And then it would immediately shoot back down to 0. Okay? So this behavior is important. But you have to realize that this 50 volts is not being supplied. It's just that node, we call it, that node is driven to 50 volts, or it's pulled up to 50 volts through the capacitor. And it's only pulled up because the capacitor will not allow an electric field to form across it instantly. And if we left that at 0 and the other side went to 50, we would get an electric field in an instant, and that can't happen. It needs time for the charge to accumulate. You had a question?
I did, but I don't think that's how it would work. So I was like thinking of like some of the older TVs. If you turn them on, you get like a flash of all the LEDs going off, and then it would darken, and then you start to brighten up so you can see it.
I actually have no idea how displays work. Maybe. It might have something to do with that. I don't know. I know that, like, I'm using a wall adapter right now. It has like a little power LED on there, and when you unplug it, it slowly fades. That's because of the RC time constant of whatever capacitor is on the output with whatever resistors are in there connected to that LED. When I pull it out, there's no more power, but it's still the light stays on. It's the same thing with this charger. If I unplug it right now, my light on my laptop will still stay on because whatever energy is still inside that brick, where is it? Whatever energy is still stored in the capacitors and the inductors inside this thing, it's still flowing into my laptop until they're discharged, even though it's not being supplied anymore. So you've probably seen that before with your laptop chargers. Like the light will stay on, and you're like, what the hell? There's no power. How is that even possible? This is how. All this stuff. You have a question?
Yeah, I have a question on the other circuit.
This one?
Yeah, so, for this one, I just want to make sure I get this right. Since you can't change the voltages like across the capacitor, it will remain at 0 once it pulses up, like V out A, right?
V out A will not remain at 0. It will go up to 5. Oh, no. No, I'm still talking about the wrong circuit. Yes, let's plot this one, because I keep looking at these waveforms and it's throwing me off. Let me plot these. Let's run it. We'll plot V in A, V out. Whoop. Sorry. I want to get these off. V in will go here. Oh my God. Sorry guys. I'm all over the place.
Here's one thing, not Monday.
I plotted the wrong one.
We want to be at
All I know is it's almost the end of the semester. All right. So now we got them, right? You're right.
okay.
V out will not go up initially because I put 5 here, and this voltage cannot change instantly, and this is stuck at 0, so this has to stay stuck at 0. But then I get this current flowing through this resistor. Oh my gosh. I'm going to plot that too, because we didn't even talk about currents in the capacitor circuits because I just didn't want it to get too overwhelming, but we have to talk about them in the inductor circuits. But let's run this and just add another one.
Yeah. How did you know that the resistor needed to be flipped?
Because you see the little red arrow on there?
Oh,
I wanted it flowing into the capacitor. If it's flowing out of the capacitor, everything's going to be negative.
I can tell just by looking at like the R1.
Oh, no, I can't. I think you might be able to tell because you see the little spike? The spike is on the far left. It's on the top on that, and if you rotate it, then it's on the, oh my gosh. If you rotate it, then it's on the bottom. Nope, it looks exactly the same, so I honestly couldn't tell. I only know because of the arrow. All right, but anyway, but what was your question?
Well, now I'm a bit confused. Like, so you have V in A and V out A. There's a resistor across. I was wondering why V out A has to go to 5 volts instead of like, because usually when you have a current, like the voltage drops.
Why does it eventually go to 0? Like, why does this eventually go to 5?
Yeah, instead of like, I don't know, like 4 or something.
It stays. So what happens? Let's go back to the paper now. So if I have a circuit like this, or I have a resistor connected to a capacitor, and let's say that it's connected to a pulse that goes 0 to 5, right? So when this goes to 5, we know that this initially stays at 0. That gives rise to a current. I have a potential difference across this resistor, right? So my current is going to start charging my capacitor, that current, because I know that I is equal to C dV dt, right? Where my V is the voltage across the capacitor. So if I have a current flowing, which I do here, at that instant, I start charging my capacitor. My voltage has to change with respect to time. If this I is some value, that means that it's equal to C times some change in voltage, right? So my change in voltage is a positive value at that time, which means my voltage on the capacitor starts going up. If this starts going up, right, that current starts decreasing, right? So if this goes up to 1 volt, now my current is less. It was 5 over R, now it's 4 over R. It keeps going up until it reaches 5. And at that point, there's 5 here and there's 5 here and there's no more current. So the capacitor stops charging. And so then in steady state, this is 5, the capacitor is at 5, and now there's no current. That makes sense?
Yeah.
That makes sense to everybody? Question?
Does that mean that an RC circuit, this specific RC circuit, that resistor acts as a short in steady state for a charge capacitor?
Wait, hold on.
Not really. I mean, It just has the same potential across it, so there's no current flowing. But it's not in that one meaning of short. Yeah.
Okay.
But like it's the same as like having a voltage to a resistor that's just connected nowhere, right? The resistor's acting like a short because there's no voltage across it, but there's also no current going through it, so it's not really a short.
Right. Okay.
But I see what you're saying. Yeah. Yeah.
Would be really dumb or kind of smart, but the way I thought for like a capacitor is like the way it acts as a short at the beginning, it's basically a resistor with zero resistance across it, so like a wire. But then as you start to pour energy into it, it increases to a resistor that has an infinitesimal amount of resistance to it. So in that case, like 5k ohms to infinity is essentially nothing in a way, if you want to do it like a mathematical way of thinking about it.
I think you're saying like basically it's acting like basically what you're saying in so many words is it acts like a short
Yeah.
in AC and an open in DC.
Yeah, something like that.
Yeah, I mean that's basically that's something else I should have wrote on here. I'm gonna put them right here. AC short, DC open. Those are important. And for AC, I mean the rising edge or the falling edge. That's the AC. It's changing. And this is an AC open and a DC short. I meant to use blue. Oh well, it's clear. But yeah, I mean what you're saying makes sense, right? An open is infinite resistance and a short is zero resistance. So yeah, it's never really acting like a resistor though. I just want you to know that.
I know that, but what I'm saying is that you can think of it in that way if it makes it simpler, is it's just going from zero resistance to an infinite number of resistance. So a number of infinity to a billion is nothing, but a billion isn't anything in that case.
Yeah. I heard you say infinitesimal something. Infinitesimal means infinitely small, just so you know. So infinite means infinite, and then infinitesimal means infinitely small. Like 0. Infinite zeros 1 is infinitesimally small.
So it'd be going infinitesimal.
It's like as small as you can imagine without being nothing.
Right. So,
Yeah, what's your question?
So, does Ohm's law not apply to this one then, considering that the capacitor or Vout is going to charge up to 5 volts then?
Ohm's law always applies to a resistor. Ohm's law never applies to anything else. It doesn't apply to capacitors because they don't have a resistance. It doesn't apply to inductors because ideally they don't have a resistance. But what do you mean by Ohm's law not applying? Because maybe I'm not understanding.
The voltage drop across the resistor should be 5 volts, so they have the 0 connected to the ground.
The voltage across the resistor is 5 right when we switch. And so that gives some current because V is equal to IR, or in that case I is equal to V over R, which in this case would be 5 volts over R, right? Well, once that current starts flowing and this capacitor voltage starts going up, right, then the current starts decreasing because of Ohm's law. Because of Ohm's law. So we'll call that I1. Let's say I2 sometime later is still V over R, but in this case it's not 5 minus 0 anymore. It might be like 5 minus 1 volt because the capacitor is charged to 1 volt. So now we get 4 volts over R. So Ohm's law is still holding true. The current is decreasing as the voltage across the capacitor is increasing. So let's go back to Spice. As the voltage across the capacitor is going up, the current is going down. You see that? And that's Ohm's law right there.
and Ohm's law only works when it's a steady state, right? Whenever it's not changing, Ohm's law would technically work if it's changing, but you would only be able to find it at a specific point.
Right, so this right here, I have the output voltage, right, and I have the current, and they're changing inversely to each other. And that's because, so let me plot V in minus V out, so you can see that, because that's what we care about here. So let me go V in minus V out. Oh, that's wrong. V out A. What in the world happened?
Delete the string. Yeah, you hit delete.
Oh my gosh. Okay. All right, so there you go. There's V in minus V out. That's the difference across the resistor, right? And that's what we care about for Ohm's law. Here's the current. They have the exact same behavior. right? That's Ohm's law. Ohm's law holds true for every single point. That makes sense?
Yeah.
So if I take this curve, V, and I take I and I multiply it by R. So if I take this I and I just multiply it by R, what's R? 250. I should get the exact same trace. See, I have 5 volts here, and I have 5 amps here. It just didn't do the units. I don't know how to put ohms in there, but those are the same now. That's Ohm's law right there. You see it? So it is happening, but it's happening for the resistor. The capacitor has its own set of things going on that are causing this exponential behavior, but Ohm's law is still holding true for the resistor.
Yeah, but what I'm saying is that if you wanted to like calculate it using Ohm's law, you have to pick a specific point and then do it there, because it only works when it's a steady state system. It doesn't work if it's an AC system.
Right.
Yeah, that's what
I mean, it works. I want you to. You can't use it to solve problems,
Yeah.
though. Yeah. I mean, at any given point, it would work.
Yeah.
But you don't want to do it that way.
Right.
You have a question? You look confused.
I'm confused on what he's saying.
He's saying you can't use Ohm's law, like V equals IR, to solve these problems. I think that's what you're saying. Is that what you're saying?
You can't use Ohm's law, like, you won't be able to graph with using Ohm's law. You can find a specific point, if you want to find, okay, in 6 uniseconds in, at this exact point.
Uniseconds. I know what you're saying.
I'm not very good at speaking.
But the problem is, you wouldn't be able to use Ohm's law to solve this problem anyway because you need to know the voltages. I know what you mean. He means you can't. You're not going to sit there and plug in V equals IR for every data point on this curve. But you wouldn't be able to do that anyways because you don't know what the data points are unless you know this curve.
Yeah.
So you couldn't even do this unless you knew the Fife equation. Does that make sense?
I don't know. But okay.
All right.
I understood this until you guys started talking about Ohm's law and stuff, but I think what some people are confused about is we're used to looking at a capacitor there as a resistor, right? And so it's a voltage divider. So let's say that capacitor was a 250 ohm resistor, right? V out A would be 2.5 volts. And so people are getting confused because it looks like that, and so you would think V out A is 2.5 volts, right?
Oh, so you're saying people are just used to seeing the circuit in the same configuration, so they think that this should act like a voltage divider even though the capacitor is nothing like a resistor?
Yeah.
Is that true?
Maybe not, but that's like the vibe I'm getting from some of the questions.
Oh, okay. Maybe. I mean, the bottom line is that's a really bad train of thought if you think that just because it looks similar that it's going to act similar. Capacitor is completely different from a resistor. And if I were to redraw this circuit, I could just draw it in one straight line. Like I could draw this. I do it this way because it makes it easier to put it on a piece of paper. But if I were to just go like this, well, that's not what I wanted to do. If I were to just go like this, that's the same circuit. I think you'd probably be mad at me.
Thank you for not doing that.
What? Why isn't it going up?
Because you have the wires, you're moving the whole wire.
There you go.
Okay, so that's the same circuit. That's the same circuit. I mean, it's identical. It just looks horrible. I mean, it wouldn't be beneficial because that's not how circuits look. But
It's right, but you're wrong.
I mean, it's literally the same thing. There's nothing different about this than there was about this.
You're right, but it's insulting.
Let me go back to what we had.
Thank you.
Okay, anyways. Yeah, so don't... I said this at the very beginning. Don't get caught up in the way things are drawn because it doesn't matter how they're drawn. It matters how they're connected. So don't... If that was the case for anybody, don't look at this and go voltage divider because it's not. It's not a voltage divider. A voltage divider only if these are both resistors. However, when we get into AC, we're going to be looking at this, and this will act like a voltage divider because of the impedances, but that's completely separate. Yeah, sure.
Would you be able to show us like what it actually would look like?
What would actually look like?
What it would actually look like?
In real life? This is exactly what it would look like.
Whoa.
The thing is, in real life, circuits are never this simple. But they do draw it with the sources all the way on the left and the outputs all the way on the right. So this is, I mean, there's only one component in between. but real circuits look like this. I mean, this is what it would look like if you were looking at like let's say you bought a filter, an RC filter data sheet. Would have the R here and the C here and the output just like this. I mean, it would look exactly like this.
Do you have a breadboard?
Oh, you mean like a real circuit?
Yeah.
Oh, I don't have the components on me. I mean, I could. You know what I want to do is I want to make a video of like an RC circuit and show you the time constant on the oscilloscope. So an oscilloscope is basically, if you don't know already, it's like a test equipment that can plot waveforms, like real waveforms. And so if I were to plug in, a pulse source and an RC and probe the output of my capacitor, we can actually see this behavior on an oscilloscope. And I can't bring it to class because the oscilloscopes are big and they stand up, but I could make a video of some RC circuits doing some of this stuff and post it if you think that would be beneficial to see.
Yeah.
How many people would be interested in something like that to see it in real life? All right, cool. I'll try and do it. All right, well, we have like 12 minutes left before I want to talk about AC stuff, so let me go to inductors. You wanted me to solve the quiz from last time. I think that would be a good, it'll give us some questions to think about. So let me just do it real quick. Let me get another piece of paper. Why is it doing that? Did everybody get tau to be 0.6 nanoseconds? No? Oh yeah, you didn't get tau to get tau is equal to L over R, not R over L. So in this case it's 3 micro over 5K kilo ohms. So if you do that in your calculator, you might have gotten like 6 times 10 to the minus 10 or something, but you gotta know how to use the calculator to move, or not. Does everybody know that there's an engineering mode on your calculator? So if you didn't know, if you go to mode, oh yeah, sorry. Oh, this is something else I wanted to mention. Okay, so for those of you who have this calculator, for those of you who have this calculator, if I do so in this case I would do 3 times 10 to the minus 6 divided by 5,000. It automatically gives it to me in some multiple of 3 for the power so that we can use the units so you don't have to think, right? So this time it gave it to me 600 times 10 to the minus 12. That's 600 pico. That's the same thing as 0.6 nano. But anything you plug in, it'll give it to you in terms of, so this would be 645K, right? So if you put it in engineering mode, it does that for you. The only annoying thing is that if you do that, it'll start doing everything with a 0 on the end, like times 10 to the 0. So I don't keep it on that often, but if you want it on, it is helpful. So yeah, it's just mode engineering. I typically just keep it in scientific. The other thing I wanted to mention is that when we do AC, and when any of you do AC, we're going to be working with complex numbers because they use the real component of the imaginary number as the DC part, and then they use the imaginary component as the AC part. So there's 2 parts to these signals. So what you're going to need is you're going to need a calculator that can do stuff with complex numbers. So if you don't have one, the cheap Casios can still do operations on complex numbers, but make sure you have one because some of the stuff that I'm going to do in the next couple weeks is going to be miserable if you don't have a calculator that can do that stuff. And it's not uncommon. Most calculators can do it. I'm sure your calculator can do it. Does it have an I on there? Does it have an I, like the complex?
I have no idea.
I'm sure it does. Every calculator does. My friend has a $10 Casio that has an I on there. That's all you need it for.
Where would it be?
I mean, it depends on the calculator. But all right, let me do this quiz before we lose time. I've got 8 minutes before I want to talk about AC. Okay, so I asked you to, given the RL, plot the waveform, blah, 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 blah. Okay. So VN goes up at 2 and down at 7. What is it, 1.8? That's my VN. 2 nano and 7 nano. All right, and then this is my current that I want to plot. Okay. This is V in. This is V out. Okay. And it goes 0 to 1.8 at 2 nano. Okay, so initially in the circuit, right? V in 0, V out 0. Okay? If V in and V out are both 0, there's no current flowing through my resistor, right? So my current up till 2 nanoseconds will be 0, right? So those equations that I gave you, there's 3 of them. There's one while T is less than 2 nano. There's one between 2 and 7. Whoops. And then there's one when T is greater than or equal to 7. Okay? So the first one for current, up till 2, it's just 0. So you would just write 0. Right? Well, what you basically say is my initial is 0, my final is 0, and that whole equation goes to 0, right, for the fife, if you were using fife. Right? So if I plugged in 0 here, 0 there, and 0 there, everything would go to 0.
Yeah, if we wrote that, is that okay?
I don't know. Did you get your quiz back? I don't know if I gave you... I probably gave you the points.
I wrote it out, and mine seems fine.
Yeah, I think I probably gave you the points. Okay, so that's 0. Okay, what do we know about the inductor? What does it resist changes in? It doesn't want the current flowing through it to change, okay? So, initially, there's no current flowing through it. When I send this voltage up to 1.8 volts, V in, if I want there to be no current flowing in the circuit, what does V out have to jump to? V out is also going to jump to 1.8. Well, I'm not even plotting V out, but V out's going to go up to 1.8 with it. So this goes up, this goes up. I get 1.8 volts. And now, like the capacitor, right? The capacitor, in that case, I was like, okay, now I have current flowing, so my capacitor starts charging because of the C dV dt equation. Well, in this case, I know that the voltage across my inductor is L di dt, which means that a voltage across the inductor gives rise to a change in the current. The current starts changing based on fife. Okay? I have a voltage across my inductor at that point of 1.8 volts, right? This goes up to 1.8, this goes up to 1.8. And my current will start going up. And it'll peak. The question is, what does it peak at? What does it peak at? What is the final value? The final value is going to be what is the current flowing in the circuit in steady state. We know that an inductor is a DC short, right? DC short. So in steady state, this is a short. So V out's going to be 0. V in's going to be 1.8, right? So that current I is going to be 1.8 minus 0 over 5K. And I think most people got it. It was 360 microamps. If you didn't get 360 microamps, does anybody have any questions about what I'm talking about with this current? Why is this the final current? Any questions? Okay, so that's 360 micro. And if you were going to write out your fife equation, you would write final is 360 micro. My initial is 0, 360 micro. E to the minus t, but I got to subtract 2 nanoseconds because of the delay, over 0.6 nano. So that'd be my equation. That's what I would write. So I'll call that I1 of t. That's what I would write right here. Yes?
So you know how you did that? I equals 1.8 minus 0 over 5k. So anytime you do that, that's going to be the final current.
Well, I'm doing that because when the circuit is just sitting here, this is 1.8 volts, and this is acting like a short. So there's going to be 0 volts here. So I know that that's what the circuit is eventually going to go to, because initially this goes up to 1.8, but now I have a current that starts flowing through my inductor, and my inductor is going to want to pull this back to ground because it's just a wire. So then if I were plotting V out, here I'll plot V out on here, V out would go up to 1.8 initially, right? And then it would go down like this, because it's going up to 1.8 with V in to keep that current at 0. But then as the current starts rising, that means that there has to be a voltage across this resistor. And that voltage is going to end up at 1.8 volts. The voltage difference across here, which means there's 1.8 volts between the V in and the V out, right? So I drew basically the dotted line as my V out. Any other questions before I do the other half? Yeah.
And so that the current equation will be different for when t is less than 2. So now it's
So when t is less than 2, it's 0, because nothing's happened yet. This is at 0, right? My pulse is at 0. If this is sitting at 0 and this is sitting at 0, then there's no current flowing, so nothing's happening. So it's 0 for t less than 2. But between 2 and 7, right, my input goes up, and some interesting things happen. The current starts rising based on the equation. And now I'm going to have a new equation for t greater than 7 nano, because now my pulse is going to come back down and something else is going to happen. All right? So now my pulse goes back down to 0. V in goes back down to 0 right here. And my current wants to keep flowing. What is my current? It's 360 microamps. That current wants to keep on flowing. The inductor doesn't want it. It wants to resist changes in current. Okay? So if I want to keep 360 microamps, well, what did I just have? I had 1.8 volts across here. So I have to keep 1.8 volts across there. If this goes to 0, this has to go to negative 1.8. Right? So if I were to plot the voltage, it would look like this. It would go down, and then it would come up. Right? It would go down to negative 1.8. Does that make sense? Is that bothering anybody? Why it goes negative? Does it make sense that the reason it goes negative is because we have to maintain the voltage across the resistor because of Ohm's law to keep that current flowing? That makes sense? All right. And so my current, again, can't change instantaneously, so it just goes like this. This is going to be a new equation now. It's going to have an initial value of 360 microamps and a final value of 0, and we plug that into Fife and we get our third equation. Does that make sense to everybody? Do we feel a little bit more comfortable about where the initial and final values come from? Anytime you're doing an RL circuit, doesn't matter whether the L is here or the L is there, the inductor current should always look like this. It should always ramp up and ramp down. It should never spike, because if it's spiking, then something's wrong. All right. Good? Bradley?
Yeah, is there a time where the inductor is like negative?
The current?
Yeah.
I mean, I guess it depends on the direction that we're defining the current. There would be a negative current. You're saying, like, does it ever do this?
Yeah.
No, it doesn't. It'll never do this. It will only ever look like this. It should never look different from this. Even in the homework that's due on Monday, it should still look like this, because this is just how inductor current behaves. Capacitor voltage behaves the exact same way, but when we're plotting node voltages, they jump because it's not the capacitor voltage, it's the node voltage, and they can jump together. So that's why. So if you want, for your own good, when you're doing capacitor stuff, plot the two sides of the capacitor, like what I did, like V in minus V out, or V out. If it's V out minus 0, you don't have to do anything. But the two sides of the capacitor, if you plot them, like this, the difference, you'll always see this. Exactly the same thing that you see with the inductor. I maybe should have explained that from the beginning. It probably would have avoided a lot of confusion. Any other questions? I'm going to go into AC now. All right. I don't think you're going to find this terribly difficult. Let me repeat that. I said that really fast. I don't think you're going to find this terribly difficult. All right, so we got about 15 minutes, a little less than 15 minutes. if I keep you a little longer so that I can, oh my, what in the, are you kidding me? This is just not it. Maybe if I throw this in there. Nice. All right. AC. Circuits. We're not really doing any circuits yet. Why? Okay. We're not doing circuits. I'm just going to show you AC signals, basically. So when we get into AC, we're typically talking about sinusoids, right? Everyone knows what a sinusoid is, a sine wave, basically. Okay? Every signal is going to be represented as a sine wave. Well, there's other types of AC signals. Square waves are a type. So here, the type of AC signals, but we're going to be mainly focused on sine waves. There's sine. There's square that looks like this. Square wave, sine wave. There are triangle waves. There's sawtooth waves. So when you take the lab, you're going to use what's called a function generator to generate these type of signals. And this is basically our power source. Our power supply is going to be able to generate signals that look like this. It can generate square waves, sine waves, triangles, sawtooth. So a sawtooth looks like this. It basically ramps up and then drops. And that's why they call it sawtooth. There's inverted sawtooth, there's inverted triangle waves. It's all the same crap. These are the 4 basic ones. Okay? We're going to be mainly focused on sine waves. Okay? So, and the reason is because they're really easy to generate. And this is how the city power works. The city power is a sine wave. And sine waves are represented in this fashion. They'll represent the voltage as a function of time. It'll be VA. It could be a sine or a cosine. It doesn't matter. We're going to talk about all that, but let's just start with a sine. And then it'll be represented as omega times t plus phi. And so there's a lot of things going on. There's a lot of variables here, but I'm going to explain what each and every one of them is. Somebody have a question? No. So VA is my amplitude. And so on my sine wave, let me draw my sine wave here. Put my axis right through the middle. This height right here from the middle, that's my amplitude. Okay? So that height, that's my amplitude. Everybody clear? It's just how, basically what's the maximum value or the minimum value. Because it goes up to VA and it goes down to minus VA. So if my amplitude was 2, it would go up to 2 and down to negative 2, around 0. It's swinging around 0. Okay? And this, don't think any deeper than this right now. This is all we're doing on the homework. I just gave you 3 signals and I asked you what's the amplitude, what's the frequency. So I'm going to explain all those things. So VA is my amplitude. Let's go to a different color. Omega is called angular frequency. And that's got basically, okay, so my amplitude's going to have units of volts or amps or whatever we're looking at. If we're looking at a current wave, it's going to be amps. If we're looking at a voltage wave, it's going to be volts, right? Omega has frequency of radians per second. It's an angular frequency. It's how many cycles are we talking about per second. So radians per second. Omega is not particularly interesting to us because we typically talk about frequency in hertz, right? You've heard of 60 kilohertz, 60 hertz. These are frequencies that are not angular frequencies, okay? And if you want to convert from frequency to angular frequency, you use this equation. This is going to be important on your homework. Angular frequency is equal to 2 pi times my actual frequency, okay? So this is my angular, and then this is my actual. All right? Oh, that's getting into the dark. Okay? So angular is rads per second, and then actual is basically cycles per second, but we just use hertz. Okay? Hertz. Wow. All right? So if I said omega was like 10,000, you have to divide by 2 pi to get my actual frequency. That makes sense? So if I gave you a signal that said sine of 10k times t, I would take 10,000 and I would divide it by 2 pi. Let me make sure that actually divides. And my actual frequency is 1.59 kilohertz. Everybody see that? 1.59 times 10 to the third? Okay. So those are two different things. I'm asking about both of them on the homework. You're going to need to know both.
Why do we need to know the angular frequency?
This is just the way that they decided to represent it. I don't know why. But a lot of times you'll see it represented like this instead, which I prefer, and that's what I'm going to use moving forward. But I wanted to start with this because you're going to need it on the homework. So VA, you'll see sine of 2 pi f times t plus phi. So they already put the 2 pi f in there for you. That's how I'll do it. So you'll see, maybe let's see, sort of an example. 2 sine of 2 pi times 1k times t plus phi. I haven't talked about phi yet. But that would be an example, right? If I give it to you like this, you know that your frequency is 1k. It's 1 kilohertz, okay, right off the bat. But typically, it won't have the 2 pi factored out already. So you need to divide by 2 pi to figure out what that frequency is. So if I just said 2 sine of 1k times t, that is not a frequency of 1k. It's a frequency of 1k divided by 2 pi. Okay? And that's how you'll typically see signals represented. You'll see something like this. Sine of, let's say, like 650 t. That is 650 is my angular frequency. It's that many radians per second. So I have to go 650 divided by 2 pi gives me f to determine the frequency of the signal in hertz, okay? So I've got my amplitude, I've got my angular frequency, I've got my actual frequency. The last thing is phi, which I haven't talked about yet, and that's called phase. It's called phase shift. Okay? And what my phase shift is basically telling me right here, this signal, this is a sine wave. I drew it a little wrong. Let's assume it starts at 0. This has a phase of 0. That means that it started right at 0, right? If I drew a signal that was shifted a little bit, like this, right? There's some shift right here between these two peaks, okay? That shift, that difference, is my phase shift. That's telling me how far is it from being like ideally 0, okay? And it's used to compare signals because this is really important in power. This is how three-phase systems work. I don't know if you've ever heard about power being three-phase power. Basically what you have is you have 3 waveforms coming from the substation. One of them is a sine wave at 0 degrees, right? The other one is shifted by 120 degrees, so it looks like this. And the other one is shifted by 240 degrees. And so you get this thing that looks like that, where each peak is 120 degrees out of phase. Every cycle is 360 degrees, okay? Where the heck did my Sharpie go?
It went under the desk.
Under here?
Yeah.
Are you freaking kidding me? Where? Oh, there it is. How ridiculous. All right, what do we got? 4 minutes? Okay, so for now, let me go into SPICE, because I think I asked you in SPICE to do it. Let's look at the homework. So I asked you to determine the amplitude, the angular frequency, the period. Everybody familiar with period and frequency, how they're related? Maybe not. Let me go over it real quick. Let's say I have a signal whose frequency is 1 kilohertz. Okay, well, F is equal to 1 over T and vice versa. T is my period. T is equal to 1 over F. Okay? And what is T? T is the amount of time it takes to make one cycle. So frequency is the number of cycles per second, right? And then basically T is the number of seconds per cycle, okay? So if I go from this peak to this peak of that waveform, that time is the period. Does that make sense? Okay. And the frequency is how many cycles are there in one single second. Okay, so now we've gone over everything. I want to go over to SPICE and show an example. I'm going to save that. So let's just go with a voltage. It's just a typical voltage source, the V, right? But what you're going to have to do if you want to sine, is you're going to do something, how we did the pulse, which was advanced, you're going to right click on it and go to advanced, and instead of pulse, you're going to go to sine. You see sine? And it has all these different things here, most of which I've already talked about. DC offset, that's talking about what is it swinging around. Just use 0 for now, okay? It's DC offset, so if I put like a DC offset of 2, it'll swing around 2 volts. It won't swing around 0. So just for now, DC offset we'll use 0. We'll talk more about those if we get to it. Amplitude, let's say I want to use 5 volts. Let's say I use a frequency. This is in hertz, okay? Notice that. This is in hertz, so that's the F. It's not the omega. This is already dividing out that 2 pi, okay? So this frequency in hertz, let's just make it 1K. We don't need a delay. We'll just have it start at 0. Theta 1 over S, I actually don't know what that is. Leave it alone. I've never used it.
I think it's an angular thing.
All right, well, for now, I'm just going to run this. I just want you to see this. Usually, we don't even put anything in the fourth spot. We don't even put a delay there. We just leave it. So this right here, we know that it's swinging around 0, it has an amplitude of 5, and has a frequency of 1K. So when I run this, I'll call it like V signal 1. I want you to see. And then when I run I'm going to run transients, just like always. We're going to look at what it does over time. And so, similarly to the last time, I wanted you to try and figure out, how do we know how long I should run for? Well, what should I make my transient time? Well, typically you want to see a couple cycles. So you would determine your period and then run for a couple periods. So in this case, it's 1K. 1 over 1K is just 1 millisecond. So let's say I run for 5 milliseconds. Dot tran 5 milliseconds. That will give me 5 cycles. Does that make sense? So however many periods you want to run for, you have to set that for your transient. And so there's my sine wave. Okay, so you see it starts right at 0, right? And it goes up to 5 and it goes down to -5. So that's my amplitude, 5 volts. Okay? And then it's swinging around 0, that's my DC offset. And so now let's mess around with it. Let me add a copy of it, and we'll call it VS2. And we'll change some stuff.
If you made the 0 a 2 instead, it would be shifted up to?
Exactly, so it would go up to 7 and then down to -3. So let's do that so you can see it. So for this one, I'll do an amplitude of 3 volts, and I'll make my DC offset 2. So it should go up to 5 and down to -1. Okay, so let's run it.
Would it do the same thing if you fed 2 volts into the negative side of the power supply rather than going straight to ground? If you had a 2-volt DC power supply.
Yes,
going
yes,
into the
yes,
negative
yes,
side.
exactly. So let's do that too.
Okay.
They should be just like the y-intercept.
No, phi is it's related to the y-intercept, but what it is it's how far is it shifted. One cycle is 360 degrees, so if it was shifted by a quarter cycle, it'd have a phi of 90. Okay, and there's a way to convert that into time, like how much is it shifted in time, and I'll talk about that next time, but you don't need that for the homework. Let me just do this real quick so you can see, Hayden. So you asked about the DC offset being 2, right? That shifts it. You see that it's swinging around 2. It's the same thing as putting a DC source here and then making the DC offset 0. So now I have a 2-volt DC added to my AC, which will also shift it up. So those two signals will be exactly the same. Oh, hold on, I have to change the name of this. VS3. Okay, and then I plot it, and it's exactly the same. So you see those two signals are identical. Right? Okay. I think the only other thing that you need for the homework is phi. So real quick, let me just show you what happens if now that I have these two that are identical, let me do one of them with a phase shift so you can see that it'll shift it out. Delete this pane, and then, so they're stacked on top of each other right now, so you can't see the other one. If I take this one and I go give it a phi of, let's say, 25 degrees, it'll shift it 25 degrees to the left. You see that? Or to the right, sorry. So that's what the phi does. It's telling us how, we use this to determine how far off our signals are from each other. And it's important because when you take voltage times current to get power, right? Power is equal to I times V. When they're not overlapping perfectly, we lose some power. So it's really important for power But yeah, just for the homework, I asked you to basically tell me what all of these are. Frequency, period, angular, amplitude, and phase, given some signals. And then I said using voltage sources and transient sims provide simulations showing 5 periods of these waveforms. So you're going to determine what's the amplitude, what's the frequency, yada yada, and then you're going to make a source in LT Spice exactly like I just did and run for at least 5 periods. Okay? Is that clear?
Yeah.
Question?
5 periods is
5 cycles. 1 over F. F over 1 is just F.